Okay, so today what we will do is we will start formally talking about Lie algebras. And here, let me just remind you that the way in which we arrived at this notion is the following. We had introduced operators xj, which were eta jk alpha del alpha j. Sorry, wrong notation. Eta kj alpha del alpha k. And we saw that xj and xk as operators had this nice commutator bracket in terms of the structure constants L, XL. And then we say that, okay, on our group, we have special subgroups, the so-called one-parameter subgroups. Not one, but multiple one-parameter subgroups characterized by the tangents at the origin. So if you know the tangent at the origin, you can actually find out what this entire one-parameter subgroup is. So this one has a tangent, and so on. So these tangents tell you exactly what this one-parameter subgroup is. And then we define an operator which would essentially tell you how...
Sir?
Yeah. Sorry.
Sir, I might have missed something in previous lectures, but I wanted to just confirm that these tangents that we are talking about, they are only like the tangents at the origin.
Yeah, right. Because when you remember, these tangents we actually introduced via their components, right?
Oh, yes.
And the components essentially were d alpha j d sigma.
Yes, sir.
At sigma equal to 0. Right? These were the TJs.
Yes, sir. Oh.
And that, of course, meant that you were talking about the tangents to the corresponding image curves here, or mirrored curves on the real space. And these tangents were, of course, being calculated at the origin, which means that for the original group, these curves, the A sigma curves, which of course are curves on the group, they are the tangents we're talking about, are the tangents at the identity. Right? Identity is what maps to the origin.
Yes.
So whatever is incorporated as whatever is the origin in terms of this one is actually the identity.
Yes.
So you talk about, yeah.
Sir?
Yeah.
So if these are tangents at the origin, so in effect we are like getting information about the whole group by just looking at the origin.
Not the whole group, but you're close. The idea is, in effect, at least there's a region, there would be some neighborhood around the origin for which complete information can be obtained from the tangent vectors to one parameter subgroup passing through the origin and tangents at the origin. And that's perfectly right. In fact, that's exactly what gives rise to this notion of Lie algebra, which basically is confining things close to the origin. If you say close to the origin, you get to know everything about almost the entire Lie group, but not the entire Lie group. We will come to that. But a lot of information about the Lie group can be obtained just by seeing what is happening very close to the origin. That is true. And that is the reason why Lie algebras, which basically are in differential geometry language, they're nothing but the tangent plane to the Lie group at the origin, at the identity. Okay. So the one tangent plane essentially has complete information about, if not the entire manifold, but a large part of the manifold at least. And exactly in what sense is that enough or it's not enough, we will come to that later. Okay. So your point is actually correct to an extent. And because we expect the tangents of the origin to have so much information, we introduce these operators which essentially talked about how fast would a function on the group change as you moved along a one-parameter subgroup which has t as its tangent at the origin. And we defined it as minus tj xj. And found out that what would happen is that the commutator bracket, again, this is again just the commutator of two operators, of the operators eta t and eta u, will turn out to be eta for some vector. It's also an operator which talks about the rate at which things will change along some OPS, some one parameter subgroup. But that one parameter subgroup has as its tangent at the origin this particular vector t bracket u, which we defined, or which we actually sort of wrote down from here as this particular entity. Okay? So, but basically, if you know the components of the tangent vector t and the components of the tangent vector u, and you know the structure constant of the group, using them, you can reconstruct this bracket. Now, this is a sort of more abstract thing. Here, it's not a commutator. You're not multiplying t by u and subtracting ut. All you're saying is you can define this bracket between t and u in this particular manner. And what's very important is if you start with this thing, and form a double commutator, this again is still a commutator, and do a cyclic sum, cyclically changing t, u, and v, you're going to definitely get 0. There's no question about that. That's pretty straightforward. On the other hand, it's also easy to see from here that this is actually the same as eta of what that implies is that this abstract Lie bracket that we have defined between tangent vectors, well, I should really call it an abstract thing. It's a pretty concrete thing at this stage. The only reason I'm calling it abstract is to differentiate it from a commutator, right? I'm not saying this is tu minus ut. I'm just saying this is some way in which you can define a product between two elements. We'll also obey this relation that if you take this thing and cyclically change t, u, and v and add up the results, you're going to get 0. Is it okay with you, all of you?
Yes, sir.
And either from the original Lie brackets or from the fact that this TUV bracket obeys the cyclic, this cyclic sum equal to 0, you immediately get a condition that is the structure constants cannot be completely arbitrary. We already know the structure constants must have obeyed this, antisymmetric in the lower two indices. In addition to that, the structure constant has to obey CJKL, CL, MN, let's say, plus, now this will be a cyclic change between K, M, and N. So, M, NK, CJ, the L's, and the J will be, J is a free index, L is a dummy. They will not be affected in the subsum. But then you have N, K, M. This sum has to be 0. This is a result of, this will work, of course, for all J, all K, all M, all N. Saying that it works for all L, of course, doesn't make sense because L is not even an index here. L is just a dummy for the summation. Okay. Now, it turns out that although this is something we said we are not going to do, we are going to do that only through assignments. This reconstruction of the group product from the structure constants Of course, there also you might ask a question. If I just give you some arbitrary bunch of structure constants, some bunch of numbers, CL, JKL, some R cube numbers, will you be able to reconstruct the group from there? The answer is no, you will not be. In order to be able to reconstruct, you will definitely need to obey this, the antisymmetry. You will also need your structure constants to obey this condition, the so-called Jacobi identity. But apart from these three, the three is the structure constants must be real, must be antisymmetric in the lower two indices, and must obey this identity, which we also call the Jacobi identity because it's a direct consequence of the Jacobi identity for commutators. These three conditions are all you need. Once you have CJKL obeying these three conditions, reality, antisymmetry, and Jacobi identity, from that you can actually figure out the entire group structure completely. These three conditions have to be obeyed. If these conditions were not obeyed, you would not be able to reconstruct the group. For the obvious reasons, because anything which came from a group must obey these properties. But these are sufficient. You don't need any further conditions. That's something that will be revealed only in the process of reconstructing the group from the structure constants, which we have started in the last assignment, and we'll finish in the next one. Okay. I'll just tell you one important result which follows as a result of this calculation, and that is the following. Ultimately, you want to reconstruct this quantity, right? We are still long, in fact, even if you have done the assignment, which I don't expect you to have completed by now, but even after completing the assignment, you will only be halfway there. Because we have just managed to solve a part of the thing and found xi and eta. From that, we still have to find f. But you will find at the end of the calculation that f can be written down in a manner which will only involve alpha, beta, and the CJKLs. It will come out as an infinite series. So we may not be able to express that in a finite, nice form. But the only thing is that you will need are, apart from alpha, beta, the coordinates, which of course will be needed. They are arguments anyway. The only other ingredient you will need are CLJKs, nothing else. And in particular, if CLJKs were all 0, then F alpha beta would have to be alpha plus beta. When I say have to be, I mean because remember we are actually using canonical coordinates of the first kind. Once you make that choice, and if CLJKs are all 0, then the only possibility is you have F alpha beta equals alpha plus beta. Nothing else is possible. In other words, for abelian groups, CJKL will be 0, that's very easy to see. But the converse is also true. If CJKL is 0, you must have a group which is abelian. And if you have non-zero CJKLs, the group cannot be abelian. Okay? I'm not writing down the form here because that's something we're going to derive later. I'm just telling you this result, that this thing depends only on CJKLs and nothing else. Okay. Right. So now let's talk about all this. We have not talked about Lie algebras yet. At least we have talked about Lie algebras, but we have not formally talked about Lie algebras yet. We just said, starting from a Lie group, we can have things like one parameter subgroups. We can have tangents to them. The tangent essentially dictates most of the thing. And the tangents obey certain properties. Especially there is a product between the tangents, which is defined via this rule. And that product is a rather nice, decent product. It obeys certain properties. Now, what we are going to do is essentially we are going to generalize these properties of tangent vectors to one parameter subgroups for a Lie group into this general concept, which is that of a real Lie algebra. We will meet complex Lie algebras soon via a process called complexification. But the Lie algebras that we get from Lie groups are all real Lie algebras. So what is this? It's several things. It's a real linear vector space, which means, of course, you can take two elements from this Lie algebra, add them together, or multiply them by constants and so on. All that you can do. In addition, so this notation for the product is something you borrow from, something you borrow from commutator brackets, which is a map from L cross L to L. So it takes two elements of the Lie algebra, returns another element. Now, this is not any product. This product has certain properties. Now, to qualify as a product on a vector space, this product must be linear. In other words, if it's a T and U, you give T and U plus V, you get T and U plus T and V. Okay. This is nothing, there's nothing to do with Lie algebra. In any algebra, you must have this. The product must distribute nicely over the sum, which is defined in a linear vector space. Okay?
Sir?
Yeah.
This Lie algebra is not a general algebra on the Lie group, right? Like there can be other.
No, first of all, the Lie algebra is not on the Lie group at all. The elements are not Lie group elements. The T's are not group elements. Okay? Right? The T's are tangent vectors to the group, to curves on the group. But tangent vectors are not elements of the set itself. Number one. Number two, these tangent vectors form a vector space, right? And they are not a vector space just in the sense that they can be added or subtracted. There's also this additional very important property that you have a product defined on them. And these two together, if you have a vector space and a product, then you call this thing just a vector space and a product which distributes nicely over the sum in the vector space. That's called an algebra. Okay?
So it's over the tangent vector space.
In this case, in the context of the Lie group, is the tangent vector space to the identity. Okay? However, we are talking now. Instead of, you may not even mention Lie groups when you talk of Lie algebras. I'm saying I'm just borrowing those properties that we have already seen to define a Lie algebra in the abstract. This definition can be made without reference to any Lie group. Do you understand what I'm saying?
Okay.
So this is just, if you have a real linear vector space. So here I'm not saying that the linear vector space is the tangent plane and the identity of a group. If you have a real linear vector space, period, any real linear vector space will do. And in addition, you have a product defined on that vector space. A product is something which takes two elements of the vector space, takes it to another element. Not just that, in order to qualify as a product, it must be linear. In other words, things like TU plus V must be TU plus TU, or T times CU. I'm saying times because it is a product, right? It's C times TU, where C is just a real number.
Sir?
Yeah.
So the familiar thing which we are all familiar with, like the cross product, is that like a Lie algebra as well?
Well, whether it's a Lie algebra or not is a different question. First of all, it's an algebra. Algebra is, if you have a vector space and you have a product. These two things would form an algebra. Do they form a Lie algebra? That comes later. Okay? You got my point.
Okay, so the Lie criterion is different.
Lie criterion we have still not specified. We have said you have a product which behaves nice. A product, after all, the basic property of a linear vector space is linear combination. This product must play nicely with the linear combination. right? If it didn't do that, it would not be something I would call a valid product on this linear vector space. But once you have that, these two together form what is mathematically called an algebra. There are many kinds of algebra depending on the properties you put on the product. You understand that?
Yes, yes.
Okay. So right now we are not talking about Lie. We are going to talk about Lie algebras, of course, but I have not completed the Lie part of the definition yet. It's just the algebra part that we have stated. Okay. So, for example, you are actually right in the sense that you can think of the cross product with a in three-dimensional vector space as a Lie algebra, but we'll see that because we'll have to talk about what properties the Lie bracket has. But another kind of algebra, not a Lie algebra, but another very important kind of algebra is what's called an associative algebra. So what is that? That's one in which the product is associative. That is, you have a vector space, you have a product on the vector space, and A, B, C is the same as A, B, C. Can you think of an example of an associative algebra? There are many, but you do know one is very familiar to all of you. Yes? Okay, the bunch of all square matrices of the same size, say all 3 by 3 matrices or 5 by 5, any bunch of n by n matrices. Do they form a vector space?
Yes.
You can add two matrices together, then multiply a matrix by a number, and all those standard properties of matrix spaces, of vector spaces are obeyed, right?
Right.
But with matrices, you also have a product. If there's matrices, the square matrices of same size, then that's a pretty well-defined product which gives you a matrix of the same size, right? Always, you can always multiply two matrices. Whether you can invert them or not, I'm not even going into that, but you can always multiply them, right?
Right.
And that matrix product is always associated.
Yes.
That's one example, a very important example of associative algebra. It's a kind of algebra. There are many kinds, not just. You could call an algebra commutative if the product is a commutative product. AB is always BA. You would call a product as algebra associative if the product has an associative property. Okay? Yeah? Now the question is, when do you call an algebra a Lie algebra? That's when the product has these properties. Okay. One is for all UV belonging to L, UV equals minus V. So it's anti-commutative. Okay? Or there's an anti-symmetry or anti-commutation law. You're going to become a minus sign. That's one important property of the Lie bracket. It's going to be a Lie bracket. A product is something which takes in two vectors, returns another vector in a linear fashion. But here you have this additional demand that it must be anti-symmetric and it must obey the Jacobi identity, which is for all UVW belonging to L, these double commutators must add up to 0. Okay? Yeah? So these are the defining properties of the Lie bracket. any bracket, no matter where it came from, okay, no matter where it came from, no matter what its origin was, if it obeys these properties, you would call it a Lie bracket, and the corresponding algebra would be called a Lie algebra. So that's the abstract definition of a real Lie algebra for you. The Lie algebra we talked about was the one which we got from a Lie group by only looking at tangent vectors to one parameter subgroups at the identity. Okay? But that was a specific example. All we are saying, a Lie algebra just has to obey these properties. That's it. Right? Now, there's one very important way in which you can always obtain a Lie algebra from another one. Say, if A is an associative algebra, so suppose you have an associative algebra. So one example of an associative algebra we have just given, the set of all square matrices of the same size. But you can also think of, well, if something works for operators, for matrices, operators should not be far behind, right? You can also think of operators essentially forming an associative algebra, right? When you have any situation where product means do one thing after another, must be associative by its very nature. So operator algebras, where the product really means apply one operator, then apply another, right? That has to be an associative algebra. But let's say you have some associative algebra from somewhere. So let's say the product here. In this associative algebra, let's say there is a product which we call star.
Did Sir get disconnected?
I think so.
Sorry, lost power in between. So I'm now back, right?
Yes, sir.
Yes, sir.
This is not a network outage, this is a power outage. Anyway, thankfully, that's rare here. Okay, we were saying this is what we were saying before we got cut off, right? You have seen up to this much.
Yes, sir.
Okay, first of all, is a Lie algebra associative?
Not necessarily.
Well, actually, no, because associativity would have meant this and this are actually equal, right? Which would have meant that these two together would have added up to 0. Isn't that right?
Yeah, one is the negative of the other. So
yeah, one has the negative of the other because these two are negatives of each other definitely, right? So unless you, of course, you can say that okay, you could have a Lie bracket which vanishes identically, in which case it's also associated. But except in the non-trivial case, this three-term sum which you have to define in the Jacobi identity is a clear-cut sign that your algebra, the Lie algebra that you're talking about, is not an associative algebra. Okay, you do realize that if it had been associative, this term, which is basically A star B star C, must be the same as this.
Sir, your screen is not visible anymore.
Wait a minute. Yeah. Okay, it's now visible, right?
Yes, sir.
Yes.
But these two are definitely equal to, would have been equal to each other if this had been a associative algebra. But then these two together would have given you 0. You wouldn't have needed this third term, right? So Lie algebras are not associative. Okay, they are a kind of non-associative algebra. However, if you're given an associative algebra, which is a very common kind of thing, matrices, operators, all of them have it, can construct a Lie algebra. So you can construct Lie algebra from this algebra A by this manner. Define A B as this. Okay. Now you should be able to check that this algebra that you have got is a valid Lie algebra. In other words, this bracket that I have defined is a proper bracket. So for that, you have to check that it is first of all a valid product. That is, it is literally A and B, which is sort of easy to show. Then show it's antisymmetric, which is trivial to show, right? And then you show that this actually obeys the Jacobi identity. But that you have seen several times, right? Basically, the moment you have a commutator kind of entity, if you write down the Jacobi identity in full, things will just cancel out and you will get 0. Right?
Yes, sir.
You agree?
Yes.
So, Jacobi identity will automatically follow. So in other words, if you are given an associative algebra, you can always create a Lie algebra from it. So although we said that when we talked about Lie brackets, note that we said that the bracket is an abstract operation, which has these properties. It's a product, it's antisymmetric, it obeys the Jacobi identity. We did not say it's AB minus B. But we are seeing this, that if you have an associative algebra, then if you did AB minus BA, you will get a Lie algebra from that. And it turns out, and this last part is actually quite difficult to prove, that the converse is actually true. If you're given any Lie algebra whatsoever, you can always construct an associative algebra from which this Lie algebra would follow by defining the bracket as AB minus BA. Okay? So in essence, I could always say all Lie algebras are basically AB minus, have brackets of the form AB minus BA.
Sir?
So what is the converse?
The converse in this case is This statement is if you have an associative algebra, you get a Lie algebra out of it. Right? This is a statement. The converse in this case is if you have a Lie algebra, you can actually get an associative algebra from which this Lie algebra will follow.
Sir, is that associative algebra unique or not?
No.
Okay.
It's not unique, number one.
And
number two, it may be horribly difficult to find.
Oh.
Okay, so it's not always practical.
So you're saying that in algebra can always have an underlying associative algebra from which it can be constructed.
Yeah, yeah. Hold on, I just have a call. Okay, so where were we? What we are saying is that there is, given a Lie algebra, there's always an underlying associative algebra where the Lie bracket will be really a commutator. So frankly, if you only think in terms of commutators, which you are trained to doing in terms because you have done quantum mechanics, you will not really be going wrong in a big way. Is that okay? So although we can talk about Lie algebras in the abstract, usually just thinking of AB minus BA is good enough for most purposes. But practically, it may be very, very difficult to find the underlying associative algebra. So it may not be a practical thing to do. Right? Any questions about this?
No, sir.
Okay. So then, okay. So now, a Lie algebra, we have already seen structure constants in the context of groups. Where do structure constants come from in the context of Lie algebras? The answer is simple. A Lie algebra is a vector space, right? It's a real linear vector space. And one thing which we use to describe vector spaces is, when we talk about vector spaces, what do we use most conveniently to describe it? Yes, what do we use?
Basis.
A basis, of course. So if you choose a basis on this vector space, this is an R-dimensional vector space, let's say. I'm continuing with the letter R because if you have an R-dimensional Lie group, real Lie group with R parameters, we have already seen that the tangent vectors to the one parameter subgroups there are, of course, they have exactly R components, T1, T2 up to TR, and therefore they form an R-dimensional vector space. So we are using the same letter R here. Because ultimately, although Lie algebras can, of course, be studied completely independently of Lie groups, but ultimately, the reason why we are really interested in Lie algebras in physics and almost everywhere is basically because there is a symmetry group underlying the system, which is a Lie group, and from that you get your Lie algebra. Now, once you've chosen a basis, then you can talk of the bracket in two elements, two of the basic elements. Now, what can you say about this bracket? What must this be? What kind of an object is this? Yes? Your taken two basis vectors from the bracket. Is the resulting thing going to be a basis vector, for example? Yes? No?
Should be some element of the vector space.
Yeah, it should be some element of the vector space, not necessarily a basis element. But if it's any element of the vector space, I should be able to expand this out in terms of the basis vectors. I should be able to write this as Ek times some bunch of numbers. Now, how would you label those bunch of numbers? They would depend, of course, on which component you're talking about. They will depend on K. They will also depend on which two basis vectors went into the bracket. Right? So, these numbers are called structure constants. Okay? And if you took two arbitrary vectors, T and U, let's say, and form the Lie brackets. Now, once again, let's drop the summation because we are going to assume summation anyway. Then T could be Ti, Ei in terms of components, and U would be Uj, Vj. Sorry, Uj, Ej. Again, T's and U's are just components of vectors. These are what we used last time around. And notice that because of the linearity of the product, you must have this. And now use Ei, Ej is equal to this. You get Ck, Ij, Ei, Uj, Ei, Ej. Sorry, Ek. So the kth component of T, U would be Ck, Ij, Ti, Uj. Exactly what we had talked about earlier. We had defined T, U to be that. But once you define the structure constants in terms of what happens to the basis vectors, then this follows automatically. Right? And the fact that these Ck, Ijs will obey antisymmetry and the Jacobi identity, that is, Jacobi identity for the structure constants that we wrote down earlier, follows trivially from the fact that Ei is a bracket. So Ei, Ej, Ek, if you were to cyclically shuffle Ijk and add, you will get 0. And therefore, this relationship that we wrote down earlier, this one, which structure constants would have to obey, will also be obeyed in the abstract case of an abstract Lie group. Sorry, abstract Lie algebra. Now, if you think of the connection between the Lie group and the Lie algebra, the idea is the Lie algebra essentially talks about what's happening close to the identity. So if you have two different groups which behave in the same manner, maybe there's an isomorphism, a one-to-one mapping between them, but after you do that mapping, they behave in the same manner close to the identity, then even if there are two different groups, they will actually give you exactly the same Lie algebra. Right, so it's not true that there's only one group which has this particular Lie algebra. There could actually be several groups which have the same Lie algebra. Okay?
So what did you mention about the identity?
Always says behavior close to the identity, right? The tangent vectors and the identity. What do they really talk about? They talk about a tangent vector is nothing like but a small piece of a curve, right? Effectively, that's what it is. So if you go a very small distance from the identity along the group, whatever happens there, that's captured in the tangent vectors. Tangent vectors have information about things happening close to the identity. Okay? Clear?
So for a different group, if the information behavior is same, then the Lie algebra is also
will be the same.
same.
Yeah. Okay. Right. So a very classic example of this is SO3 and SU2. They essentially behave very, very similarly close to their identity. And as a result, they have the same in Lie algebra. So when you talk of this angular momentum algebra, that is, of course, LXLY commutator is IH cross LJ or whatever. Then, of course, there's a problem that there you have structure constants which are purely imaginary, right? If you remember your quantum mechanics, is IH cross epsilon IJK LK, right? Isn't that?
Yes, sir.
Here, the structure constants are purely imaginary. But that's basically because Li, Lj would not be the elements of your actual real Lie algebra. The actual elements would be I, Li, I, Lj. If you put i's everywhere, here as well, then you will see everything works out with a minus sign. So what I'm saying is the familiar quantum mechanical angular momentum algebra is a Lie algebra, but it's really not the Lie algebra that you would directly get from SO3, the group of rotations. The one which you would directly get would have real structure constants with minus signs thrown in. That is, Lx, Ly would have been minus Lz. The IH cross is stuck in because of the extra I by H cross factor that you throw in to get quantum mechanical effects more easily. Mathematically, actually, or the I essentially is there simply because you would love Hermitian operators, that's why you put in I. Mathematicians don't really have that much of a love for Hermitian operators. To them, they're just another kind of operator, not really as important as it is to physicists. So for mathematicians, usually they don't put in that. But having said that, this particular Lie algebra is often called the SU2 algebra, right? That's what you must have heard that. Even if you have not studied SU2 formally as isospin or something, you have definitely heard of the term that is called the SU2 algebra, right? Yes, no? What?
Yes.
Yeah, but the point is actually both the SU2 and the SO3 algebra. Why? Yeah.
I'm a little confused. Like this Lie algebras, like these are defined in the neighborhood of origin, right?
First of all, which Lie algebra you're talking about? If you talk of how to get a Lie algebra from a Lie group, then you would essentially look at the behavior of that Lie group close to the identity of the Lie group, which is close to the origin of the corresponding parameter space. However, as I keep on,
but close to the identity.
Sorry?
Means we are looking at for Lie algebras only close to the identity, like how
not
the
Lie algebras close to the identity, or we are looking at Lie group elements close to the identity.
Yeah, like the tangent vector space close to the identity.
Now, by the way, a tangent vector in the ordinary space, say, suppose you talk about tangent vector to a sphere that is stuck to a point, is telling you what happens close for curves close to the point. But does the tangent vector have to be very small? Can it be large? Can a tangent vector be a large vector? Or does it have to be an inferior vector? That's my question.
It lives in a different vector space, so does its size matter?
Spice in the sense that you can keep on multiplying it by larger numbers, right? And keep on making it bigger in that sense. Can't you do that? The point really is that the Lie algebra is an entity in its own right. The vector space has vectors. If you define lengths there, you could have arbitrarily high lengths. You don't stick to small lengths only. Okay. When you talk about the tangent plane to a surface, say a sphere, the tangent plane is an infinite plane. But the tangent plane talks about what's happening on the sphere only when you confine things close to the origin, right? If you take a very long tangent, you are going very far away. The Lie algebra is a full vector space.
Yeah, my question is that Lie algebra is defined on a tangent vector space which is close to the origin. That's what we are defining.
Which is stuck to the origin, not close to. The vector space can be very far away, very big, right? When you say close to the origin, it gives you an idea that things have to be very small. The vector space can have arbitrarily large vectors.
Yes.
The behavior on the Lie group is those of elements close to the origin, close to the identity of the Lie group. That's a Lie group Lie algebra connection, but the Lie algebra in itself is a vector space. It has elements of as big a size you want. Right? All you have to do is multiply by a large number. That's allowed always. So, if you want to think of Lie algebras only as things which talk about Lie groups, hold on. Hello? Hello? Okay, I think I'm running out of time today, so we will pick this up later. But the important thing is, if you think of Lie algebras as things which come out of Lie groups, they essentially talk about what happens close to the identity. But the big property of Lie groups is behavior close to the identity dictates what happens everywhere. So Lie groups actually tell you what happens everywhere. And the one question that I wanted to address before closing, although I will not be able to address it in full, but remember, we said that the structure constants can be used to reconstruct the group. But which group? There are several groups, say, for example, SO3 and SU2. Both have exactly the same structure constants because their behavior close to their respective identities are in a way identical. We will see this in some detail in the next class, why SO3 and SU2 are actually essentially identical close to their respective identities. But the important question is, when I try to reconstruct, which group do I get? Do I get SU2 or do I get SO3? I can't get both, right? Reconstruction will give you only one product group. And the answer to that is, what I will get is the one group which is simply connected. So that's just a word for the time being, although many of you know what simply connected actually means. We will explore SO3 and SU2 a bit more in detail in the next class and show why SU2 is simply connected, not SO3. So when you try reconstructing from the Lie algebra, what you're going to get from the structure constants, which essentially define the Lie algebra, what you're going to get is the group SU2, not the group SO3. Okay. This group, which is simply connected, among many possible groups which have the same Lie algebra, that's called the universal covering group for all of these groups. In particular, SU2 is a universal covering group for SO3. And that is one of the important pieces of terminology that you will need to deal with when you talk about this connection in more detail later. Okay, if you have any questions, please ask now. If the question is about this connection between Lie groups and Lie algebras, we are going to see that again in detail. But any other questions?
Sir, you just at the beginning of the class you said that cannot say about the whole group, like the behavior of the whole group by just knowing.
Well, if it's not simply connected, we cannot know about the behavior of the whole group. That's the whole point. If the group is simply connected, then we can.
No.
So SU2 is something which can be completely reconstructed from its Lie algebra. But the whole point is SO3 and SU2 have the same Lie algebra. But when you reconstruct, you get the behavior close to the identity correct for SO3. But you don't get SO3's full behavior. Because the reconstruction will only give you the simply connected overall group. If you know that, from that you can make a lot of, draw a lot of knowledge about what SO3 is like. So knowing SU2, in fact, SU2 is what you're studying more often than SO3. Despite the fact that SO3 are the more, well, down to earth origin as a group of rotations, SU2 is more abstract, but SU2 is actually studied more because it's the universal covering group. And the Lie algebra gives you full information about whatever is happening in SU2. And from SU2, you can actually figure out a lot of things about SO3. That's just one example. There are many such things, like say SO3C, SL2C. These are all basically variants of the Lie algebra of the Lorentz group. They all have the same algebra. So we are going to talk about Lie algebras in more detail in the next class. And then hopefully by that time, hopefully many of these things will become clear. Any other questions? If not, let's stop the class today. And by the way, I will stop uploading the videos to the net because it seems that that's only encouraging people from not attending the class at all. Right? So, okay, I will upload this one. But if the attendance stays this low, I will stop uploading the rest of the videos. Then people will have to get if they're absent, they will have to deal with that in the same old-fashioned way of asking for notes or things of that kind. Okay. Bye for today. हाँ बोलिए, अब आ गया?